And then, without further ado, I'm going to pass the baton over to Nathan to talk about seasonal water level gauging for the International Great Lakes Datum update. Okay, thanks, Nathan.
All right, thanks, Meredith. Yeah, hello, my name's Nathan Wardell. I'm a managing partner over at JOA Surveys. We're a small business in Anchorage, Alaska that specializes in measuring water levels. Today I'm gonna tell you a little bit about a couple projects we did in the Great Lakes for NOAA's Center for Operational Oceanographic Products and Services, or co-ops. And the projects were in support of acquiring data for the update to the IGLD, or International Great Lakes Datum. Next slide, please. So I have a map here that shows seasonal water level gauges we installed on two separate projects. In 2017, we installed, maintained, and removed the 5 stations represented by the red stars. In 2021, we installed and have been maintaining the 10 stations represented by the green stars. These 10 stations are currently installed, and the plan is to start removing them in October of this year. At each of these stations, the objective was to collect 4 calendar months of water level data, and that data is to be spanning the months of June, July, August, and September. Next slide, please. So in general, for each of these projects, there's 3 primary phases. There's a recon phase, an installation phase, and a removal phase. During the recon phase, we do a desktop study to determine suitable sites for installing the water level sensors. This includes a review of publicly available imagery to identify coastal infrastructures for installing the sensors, reviewing historic data to identify historic benchmarks that will need to be recovered, identifying potential locations for installing additional benchmarks if necessary, and identifying the landowners. We then do a site visit to take pictures and measurements at each of the sites. And we use that information to help us develop our installation plan. While on site, we also try to meet with the property owners to discuss our plan and further help the discussion and the outreach for getting permissions for continuing the work. We also do a recovery while on site of the historic benchmarks that are available, so we can tie into historic datums and historic information. We then compile all that information, provide it to co-ops for their review and eventual acceptance for the installation plan. Once it's been accepted, we start the installation phase. Essentially consists of fabricating sensor mounts, installing the equipment, testing the equipment, excuse me, procuring supplies, going through the logistics, field crews, travel, and obtaining permissions from the property owners for both the sensors and the installation of new marks if necessary. Once that's complete, we start the field survey. That includes installing the sensor, installing the marks, running second order class 1 differential level survey of all the marks and sensors, a 4-hour static GNSS survey of one of the marks at each site. Then we, again, compile all that information, submit it to co-ops for review and acceptance. After the data acquisition period is complete, so we got the 4 calendar months of data, we do essentially the install phase in reverse. So we go out, we do a 24-hour static session, GNSS session on the same mark we did a session on during the installation. We run second order class 1 differential levels again through all the marks and the sensors, and then we remove the sensor and submit our report. Next slide, please. Now I have an asterisk here by the removed sensor because if the sensor ends up moving more than 3 millimeters relative to the primary benchmark at a site, it needs to be reinstalled the next year. And again, with the objective of collecting water level data for those 4 calendar months, June, July, August, and September. Next slide, please. So I'll just kind of go through a few examples, some examples of some of the historic marks we recovered during the field recon efforts. So this picture shows a first order class 2 vertical mark we recovered in the lawn of a residence. The mark is a copper clad steel rod monumented by the U.S. Lake Survey prior to 1968. This mark is published in the National Geodetic Survey's Integrated Database, or IDB. Next slide, please. Here's a picture of a mark we recovered near a station called Entrance to Sandy Creek, which was located in New York. This is a first order class 2 vertical mark that's also published in the NGS IDB. This mark is a rivet near a bridge abutment that was monumented also by the U.S. Lake Survey prior to 1968. Next slide, please. This is a picture of a survey disc at a water level station in Michigan. The mark was monumented by the U.S. Coast and Geodetic Survey in 1934. This one is also published in the NGS IDB. And as you can see, this mark is actually located in a building now. Not sure if it was in that building when it was first installed, probably not, but at least it was not destroyed during the construction of that building. Next slide, please. So the picture in the upper left corner of this slide was taken during one of our recon site visits. It shows the structure we identified as suitable for installing the water level sensor. You can see a few hand tools in this picture that the field crew had there. So the crew takes a few measurements in the field. We then enter those measurements into a worksheet we call estimating extremes. An example of that worksheet is on the left-hand side of the slide. We use that worksheet for determining if the site's going to go dry during extreme low water events, and then also figuring out how high above the structure we need to install a sensor so that it's not inundated during extreme high water events. We then put together a simple sketch kind of outlining the sensor and how it's going to be installed, and we put all that information into our one of our reports that we submit to co-ops. Next slide, please. We also put together a map kind of outlining, it's kind of overview map showing where the sensor is going to be installed, the marks that we recovered, and locations where we'll be installing additional marks. Next slide, please. So the sensor installation itself, all the equipment's provided by co-ops, except for the batteries that we install. This is a picture of the station for a site called Little Sodas Bay in New York. The equipment at all the sites for both projects was the same. It consists of a Sutron 9210 X-Lite data logger, a Sutron SatLink modem for satellite telemetry. There was a WeatherPack IP modem for two-way communications. There's a triple GPS antenna for precise timing of the measurements, and there's two 40-watt solar panels. It includes two 40 amp hour sealed lead acid batteries, and then the sensor is a radar sensor made by Waterlog. It's a H3611I. Next slide, please. So at each site, each site is required to have 5 marks. At least one of those marks has to be a Class B stability or higher. The marks can be a combination of existing marks that are suitable or new marks that may need to be installed. And at least one of the marks must be suitable for static GNSS observations. Next slide, please. So for the GNSS survey at each of the sites, we do a static session of at least 4 hours during installation. And then a 24-hour session is conducted on that same mark when the station is removed. All the sessions are submitted to the National Geodetic Survey's online positioning user service, or OPUS, and published in the OPUS shared database. Next slide, please. We document each static session with photos of the antenna type, so we know what model to use in post-processing. The tripod bowl, so we know the tripod was plumb. Antenna height, and we also take pictures of the tripod tip on the mark as confirmation that the correct point was observed. Next slide, please. And as I mentioned before, so at each of these stations, we do a differential level survey through all the marks and the sensor. The survey is conducted using second order class 1 equipment and techniques. We use the Leica DNA03 digital level and a fixed leg tripod. We secured 2 thermistors to one leg of each of the tripods so we could record the temperature gradient from the instrument down to about ground level. We also used a 3-meter one-piece Invar barcode rod that is calibrated and has stabilization struts. And this differential level survey is performed when the station is installed, and again when the station is removed. Next slide, please. We did a NAVDA8 level ties at sites with appropriate marks that were within 1.6 kilometer level distance of the station. All the leveling data was processed using software developed by NOAA's National Geodetic Survey. So we used Windesk, was used to properly format all the benchmark descriptions. We used Translev for processing the observations and creating level abstracts, or essentially summaries of the leveling data itself. Next slide, please. I tried to put together a couple timelines to show the schedules for the 2 different projects. So for the survey we did in 2017, we were awarded the task order in April, and it included the installation of 5 stations for that task order. And all the stations needed to be installed by June 1st and operating. So 2 months really isn't a whole lot of time to get all that work done. Somehow our crews were able to do the desktop recons, perform all the site surveys, and submit the installation plans before the beginning of May. Then in May, they're able to secure all the permissions from the landowners, and then headed out into the field, did all the installations and the survey work, and completed that all before June 1st. The reports were completed and submitted before the end of June. And then the data acquisition was complete by October 1st, so the field crews headed back out on the 1st and was able to complete the removal survey of all the 5 stations by October 12th. All the reports were then submitted and accepted, and the water level data is all publicly available on NOAA's database, Tizen Currents. Next slide, please. The timeline for the second task order was substantially longer. That was primarily due to the pandemic. The second task order included 10 stations. And it was awarded at the end of August 2019. And the stations were to be installed in 2020, collecting water levels from June through September of that year. We performed all the field recons in September of 2019 and submitted the recon reports in October of that year. Then on April 6th in 2020, we were directed by our contracting officer representative to postpone all scheduled work because of the pandemic. That essentially delayed the acquisition of those water levels for that project to this year, so in 2021. We started back up in January of this year, kind of reaching out to the landowners, letting them know we're going to be headed back out this year to do the work. The field work began in April of this year and went through the end of May. We had all the stations installed before June 1st. And then the reports were all submitted by the end of June. Data acquisition will be complete by the end of the day tomorrow. And the field crew will head out sometime in the next couple of weeks to do the removals. Next slide, please. Before we started the work in 2021, we had just completed a 2-year project installing 64 tide stations in the Gulf of Mexico. Due to the size of that project, we had developed some GIS applications and dashboards to help manage that effort. And so then we took what we learned with those dashboards and implemented those on this Great Lakes project in 2021. So this slide shows a screenshot of one dashboard that has an overview map of the project area, shows the stations, and has some information about the installation status and lists some of the photos taken at the sites. Next slide, please. One of the dashboards we built was specifically designed to manage all the photos that we take at the stations for documentation. This dashboard provided information about the number of photos at each site. It also provided information about the number of photos taken by day. And it was really useful for us to be able to track the progress while the field crews were out there. Next slide, please. This is just this is a screen grab of that same dashboard, but showing we're also tracking the photo. We can track the photos by type, and that really helped us with making sure we were properly documenting all the field components. We used an application called Quick Capture, developed by Esri, that we allowed us to pre-configure a setup so that all the photos were attributed correctly. And that really allowed us to make some of our reporting operations more efficient. Next slide, please. We could zoom into this dashboard and click on a place mark to view the photos at each site. And then look at the attributes for the photos, make sure the attributes were correct, make any changes that may need to be made in case the field crew misattributed something because it was raining or they're tired, or that happens. And then we ultimately we developed a Python script that retrieved all the photos from Esri's cloud service and then renamed the photos using the attributes. And as I mentioned, this really reduced the amount of time that we had to spend on naming photos in accordance with the co-op specifications. Next slide, please. We also developed a dashboard for monitoring data quality. So this is a screenshot of that dashboard. It shows information about the stations that are installed in Lake Ontario. These stations are currently installed. It has the strength of the signal for our satellite transmissions at the top, has the water level measurements for each site, and then it includes the standard deviation for each of those water level measurements, and then also information about the gauge voltage for each system. Next slide, please. So now I'll provide a little summary of the surveys that have been completed so far. So to date, we've completed 20 GNSS sessions. 10 of those sessions are repeat observations performed during the 2017 installation and removal surveys. The other 10 were completed during the 2021 installation survey. The table on this slide shows a summary of the peak-to-peak errors reported by Opus. The maximum peak-to-peak error for ellipsoid height was 2.3 centimeters. Next slide, please. The table on this slide is a summary of the differences between the repeat observations performed at the 5 stations installed in 2017. You see the RMS of the differences is about 1.8 centimeters for height, and less for northing and easting. Next slide, please. Now for this, a summary of the differential level survey. As I mentioned before, each mark at each station will be surveyed 2 times, once during install and once during removal. In total, we've surveyed 111 benchmarks at the 15 stations installed through these 2 projects. 40 of those benchmarks are NAVD 88 marks published in the NGS IDB, so North American Vertical Datum of 1988. And our total leveling distance in 2017 was 8 kilometers, and in 2021 we did an additional, well, we will have done an additional 33 kilometers of leveling once we complete the removal phase. Next slide, please. The table on this slide shows a summary of the leveling differences at the 5 stations completed in 2017. Overall, the benchmarks and the sensors were very stable. The largest vertical movement of any of the marks was 2.4 millimeters, and for the sensors it was 1.4 millimeters. So as you can see, all the sensors met the 3 millimeter vertical stability requirement, and those sensors were installed or were removed on schedule. Next slide, please. So all the data that's been collected or that was collected in 2017 is now published and accessible through NOAA's Tizen Currents. This slide shows the Tizen Currents page with the historic data for Lake Michigan. The 3 sites we installed in Lake Michigan during 2017 are outlined by the red boxes. A link to the data is shown on the bottom of this slide. And then once the data collected in 2021 is complete and accepted, it'll be published, it'll be accessible through the same link. Next slide, please. So that's the completion of what I wanted to present today. Before wrapping up, I did want to thank NOAA, the National Ocean Service, and co-ops for the opportunity to work on this these interesting projects, and provide this picture of a seasonal station we installed in Indiana Harbor in 2017. Thank you.
Thanks, Nathan. If anybody has any questions and they want to enter them in the chat, that would be good. We have about 6 minutes until our next presentation. I do have kind of one question in 3 parts for you. The question is, why do the stations have to be removed? Would there be any value in leaving them? Does equipment get reused?
That's a great question. So yeah, the equipment gets reused. So that's one reason why it gets removed. And then funding to maintain a station so that it provides quality data is another reason. So we install these stations, and if they're going to be in long term, there's additional costs that are associated with maintaining the quality of that data. So annual maintenance and data archival and that. So I think those are probably the main reasons why they're removed. Yeah.
Okay, thank you. Thanks, Nathan. And somebody says, is that NOAA's next research ship? And then there's a smiley face.
I don't know. I'm not sure. Can't answer that one.
Okay. Well, I'm not seeing any more questions. I'm wondering if that means we're all going to take a. Oh, there is one more. Okay. What kind of difficulties do you have in remote locations, such as vandalism?
How remote are we talking? So, we're based in Anchorage, Alaska, and we work in very remote locations all the time. And it really all depends. So like a lot of the experience that I can speak to is the work we do in Alaska, and we try to do a lot of outreach to the communities ahead of time, and while we're there to reduce the possibility of vandalism, but it doesn't always work. So we dealt with this year alone damaged solar panels, stolen GPS antennas, stolen GOES antennas, and it's not just vandalism. It's also you know, bears and muskox in Alaska, which is a different story. But yeah, I mean, I think outreach is the biggest thing that we try to do. Anytime we work in a community in remote areas, we will also hire locals so that they take a little bit of ownership in it, and they also provide measurements for us while the station's installed and we can't be there.